Hello, welcome everyone to this live session where we'll be looking at some of the 2020 papers, some of the questions from the 2020 paper. I have picked some questions that I think are quite tricky. I'll go through them. There were a few suggestions as well, but please do let me know if there are any questions that you would like me to go through. Let me first share my screen. Right, so this is the first one I would like to start with. So we are going to do question 17. This is a physics question where we have got a cylinder. There's a bike going. There's a motorbike going on a horizontal circle, and we are asked. Let me get my pen. So we are given the bike is on a radius of r. There is an angle alpha to the bike, so that's going to be important. M is the mass of the bike, and I'm highlighting what's important as I read the question. I'm highlighting the important quantities to see what I'll be able to what we'll use answering the question. So we have got our radius, the bike is at an alpha. We are given, there is something important in the question. We are told that the tires have a very high coefficient of friction. So that they can only roll but not slip along the cage. So what this means is that you have your bike here, the tires are in contact with the wall at that point, and it's as if they are stuck onto the wall. It's as if they're attached to the wall. They're not going to be sliding. They will be just rolling along the walls. So that will be important when we look at the force diagram on the bike. First part of the question, showing a diagram, the forces acting if it is to maintain horizontal trajectory as shown in the figure. So for the first part, let's say part A, we want to draw a free body force diagram. We are going to have, as always, our weight. That's going to be mg, and because there is the bike is in contact with the surface, there is always a reaction force, and we are given the angle of the bike. Oops, that's a vertical line. So this is alpha, and there will be a force, a reaction force that's pushing the bike away from the wall. So these are the forces, and we are going to have, so that's the reaction force away from the wall. Then we are going to have friction that prevents the bike from falling down as well. That's going to be acting upwards, but we will, as the question says that the coefficient of friction is very high, we'll not be considering that in the next part of the question. So looking at part B, at what minimum speed, v minimum, must the bike travel if it's not to fall down? So this is a question where we need to bring speed of the motion in. We have already drawn a diagram of forces, and I'm thinking of writing the equation of motion. So that's F equals ma. If there is acceleration or if there is equilibrium, I can equate the forces by looking at different directions, so either vertical or horizontal. So if you look at the in many cases we need to look at both directions. So we can start with the vertical direction, and we can say that the weight going down, mg, is equal to n cos alpha. So the n cos alpha, I am resolving this force into two components, and because this is alpha, this is going upwards, and cos alpha. So that's our equation of motion in the vertical direction, and we can look at the horizontal direction. We can say that n sine alpha, that's the force going towards the center of the circle, and sine alpha is going to be equal to mass times acceleration. But for circular motion, you need to remember that acceleration is given by v squared over r, where r is the radius of the circle. So from here, we are aiming to find the velocity v. So we can substitute what n is. As you can see here, there is an n, and there is also n here. From the first equation, we can get that n is equal to mg over cos alpha. And then substituting in, we have mg over cos alpha times sine alpha is mv squared over r. From there, you can rearrange. You can make v the subject, and v should be rg tan alpha square root. So this is the velocity that's required to make the bike go in a horizontal circle. If it's going slower than this, it's not going to be able to maintain a circular motion, because the centripetal force required, as we found using this equation, requires it to move this fast. Anything slower, there won't be enough centripetal force, so it's not going to be in a circular motion. It's going to fall down. So that's part B of the question. And part C is more straightforward because we are substituting some values in. We are given alpha, we are given the radius, g, and m. So we need to substitute these in. We find the minimum velocity as the square root of 4 times 10, which is g, times tan 30. And that should give you 4.81 meters per second. Let me know if you have any questions about this one, if there is anything that's not clear. Then I will look at question 18, which is the inequality question. Right, let's get that. So this is an inequality, and when I first see this question, I'm thinking, what type of inequality is this? Is this linear? Can I just rearrange? Can I just treat it the same as an equation? or is there something else I need to do? So with inequalities, if you have something like x plus 3 or 2x plus 3 is less than 5, you can basically do the same thing as you would solving an equation. You take 3 away from both sides, divide by 2, so x is less than 2 over 2, x is less than 1. So you get to your x, but instead of an equal sign, you just have an inequality. However, when you have quadratic expressions, polynomials, or fractions like this, it can get a bit more complicated. The issue is when you multiply an inequality, when you multiply both sides of an inequality by a negative number, you need to change the sign of the inequality. So if I was to make this at any stage, there was a minus sign and I wanted to, let's say, times both sides by minus 1, I could have done this, but the sign would need to have changed. So to do, when you multiply by a negative number, you know that you've done it and you can just swap the sign. However, when you have a denominator like this, if normally the first thing you would do is multiply the fraction by what's in the denominator, and it will go to the other side. So you would, if this was an equation, you could normally do something like this. You times both sides by that, it's 0, it goes away. But the issue is, you don't know whether that's positive or negative. You cannot just you cannot simply multiply two sides by the denominator. So what do we do to avoid that? Because if you multiply, it may be negative, it may be positive, you don't know that. So the rule with dealing with inequalities like this is to make sure that you're multiplying by something positive. You can do that if you multiply by the square of the denominator. So that's your rule. It always works like that. You will need to multiply by the square of the denominator. Right, to simplify this, before I multiply by the square, so I don't really particularly want to square that expression there, I am going to factorize. So you should always look for factorizations. So I'm going to say that this is the same as 2x minus 1, x plus 2 over 2x plus, plus 1, x minus 2. So this is greater than 0. Then once we have factorized, we can now multiply both sides by 2x plus 1 squared, x minus 2 squared. Because we know that this expression is positive. We are squaring it, it's going to be positive. So when we do that, we are going to get 2x minus 1, x plus 2, minus 2, so these are squared, and then we have got this in the denominator. They will cancel, of course, that's what we wanted. And on the other side, we still have 0, because 0 times anything is going to still give you 0. Simplifying, doing the cancelling, we have got 2x minus 1, x plus 2, 2x plus 1, x minus 2, greater than 0. And this is quite a nice form actually, because it's already factorized. If you think of what this looks like when you plot this, you can think of the graph, or you can think of which regions are positive, which regions are negative. The idea is, on the left hand side you have an expression, and as x varies, there will be different y values. Some will be positive, some will be negative. But you want them to be greater than 0. So you want to find where the expression on the left-hand side is going to give you something positive. So think of this as your x-axis. And if you were to plot the graph of what's on the left, you will have roots. So it will be 0 when x is -2. So I'm looking at this one is going to give me -2. This is going to give you -0.5, and so on. So the roots, I'm going to put the roots there. -0.5, half, and 2. So these are the roots. Then from these roots, you can tell in between the roots whether the expression is positive or negative. You can do this either thinking about the shape of the curve, or you can try a value. If you put, let's say, 0 is in between, you put 0 into this expression, do you get positive or do you get negative? So that's the idea. And then if you put 0, you'll get a positive value. And then once you have one of them, you don't need to try everything else. They will always alternate. So that's going to be negative, positive, negative, positive. The idea is that this is your graph. So if you are to plot this, it will be something like this. And you are looking for the positive region. So the x values that give you a positive y value. And you can see that's when x is less than -2, or it's between -0.5 and half, or when x is greater than 2. So that's the final solution of your inequality. These are the x values. If you then go back and find your original inequality, put anything that's greater than 2 into this, it will give you a positive value. Put anything between -0.5 and half, it will give you a positive value. So that's the approach to solving inequalities. Make sure you multiply by a positive number, and to do that you can multiply by a square. That way you'll always be sure that it is a positive value. Right, next one I want to look at is question 20. So let's see, that one is there. So here we are asked to find the coordinates of the points at which the line y equals m3x minus 2, so that's a straight line, is a tangent, that's important, to the curve y equals 9x squared plus 6x minus 7. We are told that m is a real constant, so we have got some quadratic expression here that's going to give you a parabola, and then we have got the line. We have an unknown in there, we have an m, so we can't really plot the line exactly, whereas even though we know the parabola, the line can be here, the line can be there. M, as you can see, m is going to change the gradient of it, and it's going to change the intercept, so we don't really know what this line is. It could be any of these things. However, we want to find when that line is a tangent. So really, the two random lines that I drew there are not going to be what we are looking for. We know that they are tangents. So more realistically, what we are looking for is something like this. That's maybe, depending on the value of m, that's one possibility. But it could be that we have got something like that. That's also possible. We don't really know yet. But just these are my first thoughts when I look at the question. I try to understand what I should expect at the end. We have got a parabola, we have got a straight line, and there's going to be a point or points where they intersect. So and the line is a tangent to the parabola. So what do I do when I'm faced with this? Like I'm saying that this is roughly how it's gonna look like, but how can I actually find those points? So there are two important pieces of information here. One is that it is a tangent. The line is a tangent. So what does tangent tell us? Let me put that on the side. So this is a very common, actually. This type of question comes up again and again in PAT. And the key thing here is that remembering that when there's a tangent to a curve, there's only one point of intersection. So if you want to find the point of intersection of a line and a curve, you solve them simultaneously. But what's really helpful is that tangent will give you only one point of intersection. So that's something we can make use of. And the other thing, again coming from tangent, is that they will have the same gradient. So these are two pieces of information. They are really useful in these type of questions, in that just by knowing this is a tangent, we are able to write two equations. We have got two starting points really. We know that they have the same gradient, so from that I'm thinking differentiation, equating gradients, and one point of intersection, I can try to solve them. But this should remind you, again, this is pretty standard. You should always think of these when you're looking for points of intersections or solutions of simultaneous equations. When you have your solution, when you have the intersection with one solution, the discriminant of the equation should be equal to 0. So this will bring us to the discriminant, and we'll see that in a sec. So let's start with the intersection. So you may not think about the discriminant from the very beginning, that's okay. But I think a reasonable step to take, if we know that they're touching each other, is to work on the intersection. So how do you find the point of intersection of a line on a parabola? You would they're both in the form y equals, so you can equate them to each other. So that's what I'm going to do. I'm going to say m3x minus 2 is equal to 9x squared plus 6x minus 7. And then I can do what I would normally do if I knew what m is. It doesn't matter that you don't know m. You can still solve this equation, and you should expect a parabola, a quadratic equation from this. So I move my terms around. I will get 9x squared plus 6 minus 3m x plus 2m minus 7. So this is a quadratic equation. You can see that this is in the form ax squared plus bx plus c equals 0. So it's a quadratic equation, and this comes in now. There's only one point of intersection, it's a tangent, so the solution of the equation, which gives you the points of intersections, will be only one solution. So the discriminant which is b squared minus 4ac, must be equal to 0. So this now gives you an equation in M. So we are looking at the coefficients. B squared, that's going to be 6 minus 3m squared minus 4 times a, which is 9, and then 2m minus 7 equals 0. Right, we can simplify this and get some solutions. We expand 36m plus 9m squared minus, we have got 36 and then 72m plus 36 times 7 equals 0. Let's simplify 9m squared. So that's 8 of them equals 0, and then we can divide everything by 9. And then that's 4 times 8, 32 equals 0. So we have two roots here, equals 0, two m values, m equals 4 or m equals 8. So what does that mean? Well, it's giving us two m values. It's telling us that for when m is 4, there will be one solution to the intersection of the curve and the tangent, and the same thing will be true when m equals 8. So that's giving us the m values, but that's still not telling us what the points of intersections are. So what we can then do is use the other piece of information, because we said we use this. That's we know that they are tangents. There's only one point of intersection, but then we can use the fact that they're the same gradient. So to use that, what we need to do is equate the gradient of the line to the gradient of the curve. So looking at the gradients, let's remind ourselves what the lines are. Let me just copy this. That's so the gradient here is, this is y equals 3mx minus 2m. So the gradient of that is going to be 3m. So we have got 3m equal to gradient of this, you do dy by dx. So that's 18x plus 6. We can then make x the subject, because we are looking for the coordinates of where they meet, where they have the same gradient, and where they meet only once. So that's why we have the two conditions. We are looking for x values that satisfies both conditions. One condition is that they meet only once, that's this, and then the other condition is they have the same gradient. X is going to be 3m minus 6 over 18, which is m minus 2 over 6. So we can now find, let's clean these. we can now find what these x values are. And to do that, we are going to use the two m values that we get. So we say for m equals 4, x is going to be equal to 4 minus 2 over 6, which is a third. And finding the x value, you can find the y value by substituting into the equation. So this is m 3x minus 2. That gives you minus 4. And then when m equals 8, you can find x to be x minus 2 over 6. So that's 1. And then y will be 8 times, you're again substituting back into the y equation, the straight line equation, 3, 1, minus 2. So that's going to give you 8. Therefore, you can say 1, 8, and we have got a third minus 4. So these are the 2 points which have the same gradient for both the straight line and the curve, and they are a tangent. The straight line is a tangent to the curve. And let's see what the next question is. Or before we move to the next question, I want to show you how these look, what this actually means. I made a rough drawing before we started the question, but we can see what these actually look like and how what m is doing here. So if we put, let's say, let's plot these. So we have got m 3x minus 2. Then the other one we want to plot is y is 9x squared plus 6x minus 7. Okay. So we have these two, and as you can see, for when m is 1, there is the straight line is intersecting the parabola at 2 points. It's not a tangent. But if you change the value of m, there will be different gradients, different y-intercepts, but there is going to be a point where you are there, which is, if you zoom in, you can see it is a tangent, and you can see that it happens at m equals 4. That's one of the m values that we found that will make this straight line a tangent to the curve. And if you keep changing the value of m, you will see that it stops being a tangent, and if you get to 8, it will become a tangent again. Oops. And that this time it happens at a different point. That happens up there when x equals 1. And that's the other solution that we found. That was the other point. And you can see that it happens when m equals 8. So that's the effect of changing m. Based on m, the straight line have different gradients and different points where it intersects the curve. Right, we can now look at the next question, which is question 24. Right, this one is a question about areas, shapes of areas. Again, this is another standard question in PAT where you have got different shapes, circles, triangles. Some parts are shaded, and you want to. In some cases, we just want to find the area of the shaded region, or in other cases, we want to express one in terms of the other. But the idea is we need to always link some known quantity. In this case, we are starting with x, which is AD, to the other lengths and areas on our shape so that we can get to the expression that we want at the end. So the first thing I do with this type of question is that I label my diagram. I put everything that I know. I'm given just that AD is X, but I will think to myself, is there anything else that we know? Can we find something in terms of X, or is there any other X's, and so on. So remembering that these are parts of circles, the X is going to be your radius. And if that's the radius of that circle, that means that this is going to be x as well. And the same is true for this one. This is a circle, part of a circle is an arc, and that makes this another radius. So that's also going to be x. So even though the question started by giving us one length, we know that actually we know three of the lengths. So they are all x's. So that's the first one that I have put there. And now then I'm thinking, okay, can I find any of these areas? Well, looking at this one, you should be thinking of area of a sector. That's a fraction of the whole circle. And then you know the triangle area. It's half r squared, half AB sine theta. But we have got it's part of a circle now, so we have the two x's, so we can find the small area. So I'll start by writing that out. So this is going to be half, for a sector we normally have half r squared theta, and then for a triangle we have got half r squared sine theta. That's why we have got half x squared theta minus half x squared sine theta. So I am taking away the area of the triangle from the area of the sector. And this gives us half x squared theta minus sine theta. So that's the small area. And then we need to do something similar to the large one as well. But we don't know this angle. So I'm going to call that angle phi, or you can call it alpha, beta, whatever you want. But the idea is, as I was saying before, we will need to find a link between them at the end, because now we can write it in terms of phi. It's the same logic. Large area is going to be half x squared phi minus sine phi. So that's the same formula, that there's nothing new there. But our task now is relating those two together, because we are not given phi. We can't give our answer in terms of phi. We need to relate phi to theta, really. Right. How can we do that? There isn't a direct link really at the moment between the two, but considering these two sides are equal, they're both x's, we know that these two angles are the same, so we can call them alphas, and that will give us that will give us the opportunity to write relationships between theta, phi, and alpha. Because now we can see they're in a triangle that links alpha and theta together. So we have got theta plus 2 alpha equals pi. They add up to 180 degrees. And on this side, we can link alpha and phi because they add up to 180 as well. So alpha plus phi is equal to pi. So now there is an indirect relation between phi and theta. We can eliminate alpha because alpha is pi minus phi there. So we can substitute it in there. Theta plus 2 pi minus phi is equal to pi. So this will give you phi equals theta over 2 plus pi over 2. So now we have linked theta, which was given to us, to phi, which is what we introduced to help us write an expression for this area. But we need to go back to what the question gives us. Right, let's do that and let's see what we'll end up with, because I'll go back to my large area and say that it's half x squared phi, but instead of phi I am going to write theta over 2 plus pi over 2. And then take away sine of phi. Again, instead of phi, I'm going to write theta over 2 plus pi over 2. So now we have got our expression for the large one. We just need to add the small area to the large area, as well as simplifying this, because you can recognize that sine of an angle plus pi over 2 is cos of the same angle. This is, if you think of a simple example, sine of, say, 30 plus 90 is going to be equal to cos of 30. So that will simplify your expression a bit. So we have got cos of theta over 2 there. And then you add everything up together. We have got the small area, which is this expression there, plus, so let me highlight them. We need to add this to that. So the half x squared can stay still out as a factor. Then we have got theta plus theta over 2, that's 3 theta over 2, plus pi over 2, that's this one. Then we have got minus sine theta minus cos theta over 2. So that's your final expression for the two areas added together. Okay, that's the last question that I wanted to do. If you have any questions, please let me know in the chat or in the comments. Otherwise, thank you very much for joining. I hope this was helpful to you, and I wish you good luck in the PUT.